Oh, thank you.
All right, sounds good. Let's go with it here. So, class, where are we at? Boom, boom, boom. We are in chapter 6. It's called the applications of integration, just like chapter 4, I think. Yeah, 4 was applications of derivatives, right? So, where are we headed with this first one? We're eventually headed to three-dimensional stuff.
Oh,
But for now, for now, we'll do 2 dimensions. And so let's see. You want to write this down probably as well here. So this is area between curves, areas between curves. And that's all you need to write down for this slide. We good? All yours for that. But what are we talking about? So remember in chapter 5, don't write this down, just kind of as a reminder. Remember, we did that in chapter 5, is that right? We went from 0 to whenever, right? Took the derivative. Chapter 6, what are we going to do? We're going to do something like this. So chapter 5 here and chapter 6 here. We're going to go like this. There's my function. And there's another function, maybe all the way down here. And we're going to do that right there. We good? So now, because we have that little red stuff is not going to be negative anymore. We good? So that's going to be just the area itself right there. So let's say, again, don't write this down.
Negative area.
So this time the area will always be positive. We're good? So this was f of x dx from a to b. Careful with this one. This one's going to be like this. It's going to be the antiderivative from a to b of your top function, whatever it is. That's the top function. Subtract the bottom function. Okay, now real quick here, you guys, want you to notice something. Notice when we're subtracting the bottom function, this will also be a positive, right? So anything underneath the curve would be positive. So this would be the whole entire.
It's net area.
The net area would be positive. Okay, are we good there? So 2 functions. What do you guys need to sort of like think about is top minus bottom always. We good? So sometimes you got to dig for that top function. Then also at the same time, you have to dig where they intersect because it could be we just want the intersection point. Okay, example number 1, the easy one. Let's jam. So writing this down if you want to. Finding the area of the region bounded above by this function. And again, I'll let you guys write this down if you need be. And bounded below by this function. And then I should tell you from where to where. So from x equals 0 to x equals 1. Good,
so we
good.
don't actually need to know the graphs, right? Not graphically.
Sometimes you may have to do it graphically because you need to find out when they intersect sometimes. Because sometimes it'll just say, give me the area between these 2 curves.
Let's go through the order.
And does it get complicated? Of course it gets complicated. That's the fun part about it. But let's start out with the easy one here. Can you guys, let's just draw it together. We're good? And tell me if I'm going too fast. Because remember, I usually write this on the board. But now that I have everything sort of preset, then it's going to go fast. We're good? So you guys tell me if I'm going too fast and just tell me to slow down. Totally fine. E to the x. Anybody e to the x graph? It's an exponential graph. And Isabel got it correct.
It's the y-axis of 1.
Okay, yeah, it's a flat line on the left side. It hits 0, 1, and then just goes zoom up in the air.
That's better than my fork drawing.
And then we have y is equal to x. We know that one. And now the question is, do they interact? So you got to be kind of mindful of like, do they intersect each other or not? And sometimes if you're not quite sure, just graph it on your calculator as well. We're good. So y equal to x, there's my e to the x. There's my x. And there's my area from 0 to 1. I'm looking for that guy right there. We good?
They don't intersect, right?
They don't intersect. Sweet. They're at 0. They're actually 1 away. Is that right? And then we go from there.
So now so it's antiderivative from a to b of.
Which is, what's a and b?
0 to 1.
0 to 1. What's your top function?
E to the x minus x.
Perfect. E to the x minus x. And all yours to do it.
Before we have to split them up?
No, because there's never a time these guys intersect. Oh yeah, you can split them up. Yes, absolutely. Split them up individually. Yep, absolutely. All right, and tell me if you guys want to write it down. As I see people writing, I'll wait just a little bit. E to the x is the antiderivative of e to the x, is that right?
E minus one.
Minus
minus.
x squared over 2, perfect. Evaluated from 0 to 1.
It's E squared. No, it's E minus 1/2.
If you're plugging one, yes, E minus,
Mhm.
yeah.
E to the
It's E
1
minus
minus 1/2 looks like, is that right? And you subtract that from e to the 0, which is 1, minus 0 itself. Yeah, so I write down all the stuff here just so we're not confused.
It's E minus 2/2.
So that's going to be e to the 1 minus 1/2, but then also a minus 1. Okay, and then again, you guys tell me to slow down if need be. Amelia, doing okay there? Some people are just kind of doing it by osmosis.
If you think of Matt, go for example, this one.
All right, e to the, oh, sorry, e to the 1 minus 3/2. There we go.
Entire semester and you just can't see it.
You can pick any CD.
It's good
You chose the right, and what's
Okay,
Yeah. I don't know.
all right.
Guessing this gets more complicated.
Oh yeah, this is
When,
fun.
Like, if they intersect,
So remember,
They
it is
intersect
always,
in the middle of your parameters, is that the issue?
yeah, and if they do, remember, we're trying to get the area between them, right? So if they do intersect, we got to flip top and bottom at that point.
So 6.1 and 6.2
Yeah.
aren't introducing any new concepts, it's just more of antiderivatives.
They'll introduce new concepts. So how do we make it into three-dimensional space?
You
Um,
just do
Get there,
three
get
antiderivatives.
6.3.
But you will not learn any new ways to do antiderivatives, right? We learned that chapter 5 is done, right? Okay, a little bit more complicated as we go. Let's go. Example 2. Now it says this, find the enclosed area. So I know this stuff intersects, and I need to find the enclosed area here.
Oh, no. That actually sounds.
All right, enclosed, and then it's going to be by this function here. Of course, a trig function. It has to be a trig function. And this function. And I'm going to go from 0, x equals 0, and I'm going to go all the way up to pi over 2. Okay, so again, you want to graph this? Probably you want to graph it on the calculator just to see what happens. Let's see. Let's graph sine of x.
Sine of x, oh, together? Oh, wait, don't they overlap every pi over 2, but we don't consider pi over 2, so we don't have to-
Yeah, I don't think it's pi over 2 that they overlap, though.
Isn't it
No, it's every pi,
pi?
right? I think it's every pi that they.
No, they're skewed. They're skewed by,
Oh,
they're
no.
skewed by pi over 2.
They overlap at every pi with 4.
Oh, pi over 4.
No,
No, they're skewed by a pi over 4.
They're skewed by a pi over 4. So let me draw.
so it's like this.
Let me draw sine of x from 0 to 2 pi. Tell me if you guys agree with that right here, right? It starts off at 0, 0.
Oh.
Yeah, sine of x goes from 0 to 1 by the time you get to pi over 2.
Cosine starts at 1 and goes. to 0.
Yes, cosine starts at 1 and goes down to 0 by the time you get to pi over 2. Oh man, what's my area? It probably shaded in would be a good idea. It's that area right there.
Yeah, it's like that.
That's
Yeah, 'cause we're only doing that first.
And that area right there. It looks like 3D glasses, doesn't it? Like with the red of the.
Why is the bottom part look? Because it's like going by the x-axis.
Sure, yeah, because if we take the x-axis out, sorry, question was why, how come we don't get this little middle area? Because it's just the enclosure of these two. And so if you take the x-axis out, this is wide open. Good there? Is that a
What if
good?
you take the y-axis?
Is it because they?
And the y-axis
overlap
out, but I already told you I go from 0 to pi over 2. So that's already enclosed. It's almost like this bar line here and a bar line right here.
them? Wait, but,
Okay.
so does it cancel out because they overlap?
Oh, no.
Okay, no.
Because I want the area that's enclosed by both of them.
Oh,
So
I
it's
see.
always gonna be top to bottom.
Technically, you only find the area of 1.
Okay,
Because
so,
they're mirror
uh-huh.
images of each other?
perfect. You guys are way ahead of the curve. That's awesome. So we have two options here. We can mirror image of each other. You can go from 0 to pi over 4. We good? But I do want to teach you a different skill. We good? That's why we're going to do it differently here. So I just want to teach you the skill of top minus bottom all the time. We good? Because sometimes they may not be symmetric. In this case, they are symmetric. We good? But the general skill is what's top and what's bottom from 0 to pi over 4.
Top would be the first one, so cosine.
Cosine is top and sine is bottom. So the way we're going to write it is, here it is, dun, 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 dun. Cosine of x right here, sine of x over here, and then it gets flipped. Now it's sine is on top and now cosine on the bottom.
You have to do each section individually.
You got it.
It'll give us the same answer.
Yep, only if it's symmetric, you can kind of think about how you want to do it, but here's a general rule at, now the question is, where does it intersect? Now you could do it by graph, that's fine, but normally if we say algebraically, where does it go? We got to solve that guy right there.
Well, sine of that?
Oh, do you guys remember? So yeah, it's pi over. We know it's pi over 4. Is that right? Uh-huh.
Degrees, where you actually
What's
try
it,
to
pi
have
over
on the unit
4?
circle.
The cosine of pi over 4 is.
Like on the unit circle at 45 degrees,
Oh, right.
and X and Y are identical.
Mhm. So if you know it, that's fine. You may have
Why
to.
is that brain functioning?
So again, not always are these gonna be trig functions, right? So if you're stuck and you kind of don't know, you might have to solve it algebraically. Are we good? Okay. Real quick here, guys, if we were to go back to trigonometry class and we had to solve this, this was actually one of the tougher ones to solve. Do you guys remember this one? Maybe, maybe not.
Like solve for X.
Solve for X.
Ouch, yeah, no.
Yeah, this was the long one. This is when you had to go like this. You had to,
That was that honors question that I absolutely failed, wasn't it?
maybe, this one is from the graph you could tell, and from your own understanding of pi over 4, you can just get the answer here. We good? But it may be that you're gonna have to do this. You move the sign over to the other side, and then you square both sides, and then you have x squared, cosine squared minus 2 cosine x sine x plus sine squared x equals 0, and it gets super crazy complicated. Are we good? So again, would you might have to do that? Yes, you might have to actually solve.
Wouldn't this just be, oh, no, because yeah, never mind.
Right. So think about your trig functions, but again, on the homework, you might have some algebra stuff you might have to solve. We good?
Hopefully it's not bad.
Not that. Okay, so let's go with it. Let's go to antiderivative. See if this makes sense. So here it is. If they were not symmetric, I'm just gonna real quick, let's finish this off. That's so pi over 4 is what you would get if you solved it the trigonometric way. Real quick, let's talk a little bit more about this here. Real quick. Do you guys remember whenever you square both sides of an equal sign, if you're the one squaring both sides, you may introduce to yourself extra answers that are not really there. Is that right? And if you did solve this algebraically, you actually get 2 answers, pi over 4 and 3 pi over 4. What do you do if you square both sides of an equal sign?
I forget, but like, no, it's like, it's not plugging them back in.
Yes, it
Technically, both of
is.
those work though.
No.
No, wait, no, because
What's the?
one of them doesn't work.
Yep.
In the quadrant.
So 3 pi over 4 should work.
No, cosine of 3 pi over 4.
Oh, no, it doesn't work, yeah, because it'll be
doesn't work,
positive and
'cause it's
negative. There has to be 5 pi over 4 that work. It's pi over 4 and 5 pi over 4 that work, right?
Yeah.
Because those are in quadrant 2.
Yeah, algebraically, if you solve this, you get both answers like that. But because you squared both sides, you have to plug it back in, and 3 pi over 4 will not work. Only pi over 4 would work in this case. Oh, and the reason why didn't I get a 5 pi over 4? Because it's not part of my domain. We're good. I'm not even looking at 5 pi over 4 or 7 pi over 4 because my domain only goes up to
But we're not looking
pi
at.
over 2. Right?
Wait, no. Then we're not looking at 3 pi over 4 either.
Yeah, we could have just got that rid of that already as well. Okay, so let's go with again. The calculus portion is here. It is from 0 to pi over 4. The top function is cosine. The bottom function is sine dx plus from pi over 4 to pi over 2. The top function is sine minus cosine dx. It'll go fast, promise.
Okay, well, that one.
So antiderivative of cosine.
Negative, no. Yeah,
Negative
just
sign.
Oh, no,
No.
No, it's just not.
just sine, perfect.
I
And-
keep doing this.
Uh-huh.
Negative sign is cosine.
Negative sign, but we have a negative front. Ever get the positive cosine then?
Yeah.
Okay, you guys talk to me if this is okay, 0 to pi over 4.
Derivative instead of the antiderivative
Uh-huh.
for trig functions? I get
Sine
really
of,
confused.
sine of pi over 4 plus cosine of pi over 4 is just 2 root 2 root 2.
Uh-huh, I believe so, yeah. Let me do the antiderivative here, so plus sine, let's see, antiderivative of sine, negative cosine, antiderivative, negative cosine,
Negative sign.
negative
plus
sine,
Well,
okay.
negative Plus, oh, negative on the end.
And then going from pi over 4 to pi over 2. Okay, tell me if I'm going too fast. Amelia, doing okay there? Okay, so plugging in pi over 4, that's easy. And again, if you want to show all your work right here, that's fine. If you just want to put in the pi root 2 over 2 at this point, that's fine too. But this is nice because this guy's just going to be subtraction from
That's just gonna be,
sine. Again, I'm writing it all out. We good? You guys don't need to write it all out. This is going to be cosine of 0. I just want to be complete with the notes in case people want to pause here. Now, this is going to be negative cosine of pi over 2 minus sine of pi over 2. And all that in parentheses, subtract negative cosine of pi over 4 minus sine of pi over 4. Again, gets crazy, is that right? Are we okay there though, with all that? Okay. The next line is probably what you would have written down if you were plugging stuff in here. So sine of pi over 4,
it's negative root 2 over 2
root 2 over 2.
plus root 2 over 2
Uh-huh. Cosine of pi over 4 is another root 2 over 2
minus
minus
0 plus
0,
1. What is it?
just
Yeah,
1, right?
yeah.
0 plus 1 is just 1 plus sine.
Plus 0
Cosine of pi over 2 is 0.
minus
And then sine of pi over 2 is 1. Uh-huh, got that. Minus
negative root 2, or yeah, minus negative root 2 over 2.
negative root 2 over 2.
Minus root 2.
Okay, are we good there?
Negative root 2 over 2 minus 1, so it's just negative root 2.
Yeah, so this case we could just put
Oh,
plus,
wait.
plus, plus.
So the negative root 2s are gonna cancel out, because we need negative 1 minus 1, so we negative 2. Right?
No, the two.
That-
No, let's see.
Plus, plus, plus.
Yeah, because these guys root 2 over 2 plus another root 2 over 2 on this side
It is gonna be 2.
is going to be a root 2,
Each of those will be root 2, that's, yeah, we switch on.
like that.
4 root 2 over 2.
And I got a minus 2 because it's a minus 1, right? And then over here, I got myself another. Okay, are we good there? So I got one of these. There's 1, there's 2, there's 3, there's 4. There's 4 root 2 over 2s. Subtract 2. 2 root 2 minus 2. Are we good? That is the area between two curves. Till this point, there was no way to get area between two curves. It was impossible. We good? Now we do. Let's see. There was one time Archimedes. Archimedes lived about 200, 100 BC. He figured out a way to get area underneath a parabola, and that was about it. That was the extent that we could do at that point. He did it by triangles, and that was it.
Of course you did.
Why was he obsessed with triangles?
The Greeks thought of triangles, again, maybe Pythagoras' school, remember, because it was influenced, but they broke up almost everything into triangles. That was the way they did it, because triangles would be the building blocks to all other figures, like hexagons.
Square is just 2 triangles, a rectangle is 2 triangles. One thing that's not made of triangles is a circle.
Yeah, or actually it's infinite amount of
It's
triangles,
infinite,
or infinite amount of regular polygons. Yeah, it's interesting. Okay, guys, example 2 done. Are we good there? Was that good, bad, ugly? What do you guys say?
I mean, it makes sense.
Uh-huh.
There's just a lot of tiny ways to mess up.
Yes,
And, like,
absolutely.
missing
On the
numbers,
last
freaking
negative
negative.
lines alone, I would just mess with the negative, yeah.
Mm-hmm.
I would probably do the math right and then just check.
Mm-hmm. Gotcha. Okay, this one is going to be next one. Example 3. Okay, a little bit more tougher. You guys can handle it because you guys are cool like that. A lot of pieces to it. Okay, guys, this is where your problems could lead you into like
How many homework
like a
problems
whole
are there for
page
this?
just into this, a lot less than normal, just
Okay,
because
good.
there's a lot more complication here.
Oh,
All right, find the area enclosed again by
Oh.
y is equal to x minus 1 and x squared is equal to 2x plus 6. Bless you, bless you. What?
Well, look, but I know it's not good.
Uh-huh.
Because why equals the square root of
You got it
2x
last.
plus 6?
Let's see if I remember. I didn't like.
All right, and again, I would say this here, just because this is not a graphing class, right? We should be beyond that. You probably grab a calculator and probably gonna graph this on the calculator, just see what it is. The only thing is x minus 1, we know how to graph that on the calculator, that's easy. Y squared is equal to 2x plus 6. How do you graph that on a calculator?
You just square root of x, 2x.
Perfecto. What we're gonna do is we're gonna do 2 of these guys here. So first things first, we're gonna say there's a negative square root of 2x plus 6, and there's a positive.
Oh, we have to do
I
both?
hate
We gotta do
that
both
so
because
much.
y squared includes both.
So I will be messing up on all this homework. Prerequisite redoing.
You're like, I just know already. You're just that.
Apologize in advance for all the homework questions that will come your way. Oh, plus 6
Ah.
digits.
I don't like
Uh-huh.
that.
So let's see, those that
Different answers.
are graphed on the calculator should have seen this right here. So the y squared
Ah.
goes like that and like that. There's my positive, there's my negative.
And the x minus 1 is just the diagonal.
And the
line.
only thing we gotta think about is moving this back. Like when does it touch the 0? If I subtract 6 divided by 2, I get myself -3. So if I did it algebraically, I would say it hits 0 at -3. And it goes off to the top, it goes off to the bottom. Okay, x minus 1.
I'm still graphing mine.
Sure. Tell me if you guys need any help with it.
Oh, there we go. The scale was just super weird.
Hmm.
Oh, those are pretty weird.
Okay, x minus 1 goes like this. Is that right? X minus 1 touches at the y-axis to -1, goes up 1 over 1, up 1 over 1. And we get ourselves a graph that looks like this. Shucks, I did not even connect it. So I guess on my graph paper, I'm gonna move a little bit more on the top, maybe make it just about like that.
So
We're
we're
good?
just looking for the place in between the two?
Yeah, so now here's our problem. I guess I'm thinking about that intersection point here and that intersection point there, right? And I don't even know what that is.
What are we supposed to do with this?
Uh-huh, here it is, guys. Again, it's the long one.
Three separate functions.
3 different functions. So let's do this here. So which one does this represent? This little top one, the positive or the negative?
Positive.
Okay, so we're gonna take the positive one, which is this one here. We're gonna take that positive one right here and we're gonna set it equal to x minus 1. Are we good?
Why?
So, because we're trying to figure out this intersection point right here.
Oh.
Now, can you find it on the graph? You can find it on the graph.
Do we want to know the-
Because we're trying to figure the enclosed area, which is right here. Here's our enclosed
Oh,
area,
I see. Oh,
blue or red, whatever it is here.
Why is it?
Oh, and then you know what? Here's my little problem. Why did I make this blue here and red there?
Did you have this bit and then you have that?
Oh,
Yeah,
no,
so notice top function here is here. The bottom function is this bottom curve. And then right here,
So like the, yeah.
yeah, the bottom, technically the curve, right? The bottom curve changes into this function here. Oh, man. So I got to figure out this in order to split my
Oh.
We didn't know the intersection of both.
intersection. Yeah, indeed.
Yeah.
You have to math.
Oh, it's not even that.
You got math.
You have to do it twice again, because you have to do the blue,
With the
and you could do half of the blue if you wanted to. Just half of the blue, because you know that those are mirrored, and
Uh-huh.
then do.
Jamming. Okay, Isabel has a good
What?
point here. So Isabel says this, you know these guys are symmetric, is that right? Could you go from 3, you still got the intersection point, right?
Right.
But you could just take the top function minus y, right? And you could just double this area. Are we good?
Right.
Instead of trying to figure out this area here, because
Yeah, so we
we
can
have-
just use the plus.
yeah, so
No,
that,
'cause
because these
some
guys will be
direction-
symmetric anyways, right? They
still
should be,
need-
right? Because one goes up and one comes down, is that right?
I don't think they're the same.
I guess, yeah, no, they
Yeah,
are,
no,
because
they are the
they
same.
are, okay.
The question is, we still need to know the intersection point anyways. So we can-
Yeah, we still got to know the intersection point. So I did is, just because my notes already set up here, real quick here. I did this intersection point first, so let's do that one real quick here first. I think, yeah, I think. So let's jam.
Two coordinates.
So this guy's the positive, that is
Just solve
the negative, and anything beyond that is gonna be this
Oh,
times
this is
that.
solving the X coordinate. Now, how do we solve the Y?
Ooh, okay, let's see, let's figure out when they cross. Let's figure out this little piece right here first. So those two change, is that okay? Those two change at that point right there.
Five. You subtract the X squared minus 4X minus 5, then you factor it out.
Oh, you can just back that up.
It's minus 5 and X minus 5 and X plus 5.
Hmm.
So it's 5 and negative 1.
All right, how do I know that's
How
a
did I
negative
know?
one?
Well, we solved for that intersection point, and we got 5 and negative 1.
That can't be right.
did negative 1, interesting.
The rest of it are math wrong, which is.
You,
No, hey. There's another intersection point where is that?
Oh, you're right.
That's the negative. Is that the negative 1?
So if we do that, let's try it. Notice what happens here.
No, that's the other intersection point. That's the one
Uh-huh.
over there.
So let's go with it. So I'm trying to find this guy here or this guy here. Let's see. I'm gonna try to figure out that right there. And what is this right here? It's 5.
Oh my.
Okay.
Is it 5 and negative 1?
Perfect. How do we find it? Let's do it. So what we're gonna do is we're gonna set this up.
Couldn't be.
We're gonna set the negative.
That's one.
Amelia, doing good still? Okay, just making sure you guys, just checking up on you guys here. So I'm gonna try to figure out this intersection point right here, right? It's where this negative 1 touches the X minus 1. And if I do that, I'm still gonna have to square both sides. And if I do that, I still get the positive values as well. This gonna be X squared minus 2X plus 1, is that right? Okay, so let's move set equal to 0. I'm gonna move this 2X and the 6 over this way. So minus 2X and minus 6 will give me that. And if I take the factor form of each one, two numbers, multiply negative 5, add to negative 4. Da-da-da-da. Solve for 0, each one of those guys. Perfect. So I get my negative 1. I know what that means. And then my 5, I already know what that means too. That means my intersection point is between those guys here. Okay, so let's write this out. Can you guys, give you guys 30 seconds. Can you write down the antiderivative process? Let's do it together. Let's do it together. Go back to look at our graph first. Now we know that the points are negative 1 and 5. So jump back to here. There's my negative 1. There's my 5. So here, easy. I'm not going to do it the shortcut way. We're good, but you guys can do it shortcut on the homework. All right. This piece right here. Top one is this one.
only doing one. Because then
Top
we don't
one's
have
bottom.
to do the plus, minus, add, divide, subtract thing that we're learning right now.
How do we only just do?
You do either, I would do the positive square root of 2x plus 6, and then take your area you get from that, by taking like the antiderivative of that, and doing that process that we already know, and multiplying that area by 2.
Yeah, let's do it and we'll see.
'Cause you don't have
We'll see what
negative
happens
area
here.
in this
Yeah.
anymore.
It'd be interesting to see what happens here. Oh, let me run through this again real quick here. We did this already. Let's set up the antiderivative. So looks like we're starting at negative 3. Is that right?
Yeah.
Start off at negative 3. And we're going up to negative 1. The top function for us is the positive.
Where are we going? Oh, we're just doing that first blue section.
Positive.
And then your top and bottom. functions.
Subtract a negative of that one, but subtracting
so
negative is
just
another
two-
positive. Is that right?
So it's just 2 of them.
So
We can-
Isabel,
we
look
can
at
take
that.
this further.
I think if you combine them, you're gonna get the same thing that Isabel was talking about. But let's go to the next one here. So from negative 1 to 5, right? What's my top function?
Square root 2x plus 6.
Square root of x plus 6. Bottom function. And then we need to put this in parentheses because it's two different pieces, right? In that function. Okay, guys, that's what we gotta undo. Ready? So let's do this one. We can combine together as negative 3 to negative 1, 2 of these guys. So Isabel, check this out. Your little, if you just stick this 2 out in front, it'll be the same thing Isabel was saying, right? It's 2 of these undoing the other part. Okay. So I'm gonna do this by parts because this gets too crazy. I'm just gonna leave, let's do this part here first and then we'll combine them later. So you guys talk to me 2 out in front, -3 to -1. And how do I undo this little guy right here? U substitution, absolutely. U is equal to 2x plus 6. Derivative would be awesome. Okay, so I'm gonna move the 2 back in. And I'm gonna set it up as it is from -3 to -1.
2u, 3 halves of 3.
Yeah, I just like to write it one more time with the big old multiplication symbol. And with a 2dx, we're good? Then I know exactly what I'm plugging in. So now I go from -3 to -1 of the square root of u du.
Oh, that's the thing that I forgot on the test. Cool, okay, we're good.
Now we know.
No, it was part of it. It's the 2dx bit that, well then.
I forgot calculus. Same one.
Okay, let's see. This is, you guys help me out here. This is u to the 1/2 now, right?
Yeah.
U to the 1/2.
We
So what is
have-
the antiderivative?
So 2u, we have it.
Perfect. Okay, antiderivative would be u to the 3/2 over the reciprocal of that. So 2 and the u in the bottom, going from -3 to -1. Our limits of integration are in terms of x, is that right? We can change it if we like, is that right?
Doesn't probably should.
I'm gonna keep them just for, because these guys are already set. I'm gonna have to change back into x values, and then let's figure this out. Let's put them in here. So -1 goes on top. -1 times,
So if it's a square root cubed, wouldn't it just be that thing squared?
but you gotta take a square root of that thing and then cube it.
Okay, so square root of 2x plus 6 cubed would be square root times square root times square root. So we end up getting 2x plus 6 times square root of 2x plus 6, right? Because the first square root by the second square root is just gonna be 2x plus 6. But then multiplied by the third square root is gonna be times root 2x plus 6. You have 2x plus 6 times root 2x plus 6.
So you have 2x plus 6
Ooh.
times 3 plus 6 squared.
No, because you have a root.
What is
It's
the
over
root?
2.
So you gotta take the square root first,
Yeah.
right? Then you're taking the cube
Oh,
root
right.
off of
Square root
that,
2x
but you don't know what the
Cubed.
bottom value is. That's the problem. Let's try.
Oh,
-3 in here, -3 times 2 is -2. -2 plus 6 is a
We can plug in
is a
numbers.
4, is that right?
Yeah, oh, then it's just 2
Yeah,
cubed, so
square root
it's-
of 4 is a 2, and 2 to the 3rd power? 16 over 3, or 8 times 2 over 3, minus
Okay, -3 times 2.
-3 plugged in there.
0. Oh, I went
0.
zero.
Oh, man.
Minus 0.
Okay, so for that first one is 16 over 3.
Second one.
Second one. Second one is this one right here. I think we went from here minus this, is that right? So I just multiplied that in.
We just do the same UE substitution?
Yep, now we have to separate these guys out, right? Because we go this one to that has to be separated from everything else.
We can't have an accident.
Yeah, in fact, let's kind of just show the fact that we are going to
Oh, we're going to do to one.
each of those pieces, just so we can do like all of them separated, we can kind of just do it that
So we
way.
have to have X, yes?
For the last two, we really didn't need to use substitution, but for the first one, we had to use substitution, so we would have to separate those out for sure.
Okay, do we have to have DX on the middle one?
Oh, yes, so I'm sorry, DX.
Okay, so the U substitution is the same as last time, so it's 2x plus 6.
Uh-huh,
V of U equals 2, so we just put the 2 over 2 in front and 1/2 of that. So that's gonna be 1/2 integral of root U du.
okay.
minus-
U is 2x plus 6, okay, du is 2. Oh, we don't have a 2 this time.
Wait, there's still a version of 1, so we don't have to put 2 over 2 in front of all of them, right?
No, yeah, just in front of that one only. That's why you have to separate them out. If you're gonna do a U substitution for one term or one, you gotta separate out from the rest. Because if you don't, then that 2 has to multiply into each one of those.
Plus
Okay,
also,
so,
Wouldn't
comments?
that not work anyways, because then we'd have another variable when we take the integral?
So I got myself du, and I think we could scoot that in. Can we do that all in one step? Is that fine right there?
Mhm.
Okay, this one's gonna be pretty easy to do. This one's gonna be x, so add 1 to the
X
exponent,
squared over two.
divide by 2, yep. And we're gonna go from -1 to 5. And then 1
Plus X.
plus x, perfect. And that's gonna be -1 to 5. Are we good there? She whiz, we're jamming.
The first one, so, for the antiderivative.
Yep, still have to do antiderivative of u, which I know is 2
2u,
u
3
3
halves.
halves over 3. Yep, perfect.
Oh,
Okay.
nothing. We plug in, let's plug 2x plus 6 back into 25. 10 plus 6, 16 is gonna be square root is 4, cube is 64.
Mhm.
Over 3, which is not even number, so 64. Oh, we have 16 over 3 for the first one, so that's good. That's
Yeah.
64 over 3 minus 25 over 2 minus 1 over 2, which is 24 over 2, which is 12. Minus 12 plus 5 minus -1 is 6.
Okay, so yeah, let's do this one because those are the easy ones. So let's do this one real quick here. This one would be any answer for this one?
Oh, for the first one?
For the last one
Okay,
here.
X is gonna be 6.
So you know that's going to be 5 minus a -1. That's 6. Everybody good there? Ooh, this one. Can we do this one as well? So we don't have to do it later. 5 plugged in. 25 over 2
Minus 1/2.
minus, that's going to be now a positive 1/2. Is that right?
That's gonna be 24 over 2.
24 over 2, which is 12. Okay, so I got 12 for this. I got 6 for that. Now it's just a matter of doing that one right there.
You just plug in the blue bag.
Let's go with it. So I'm gonna go that. I did it incorrectly here. So 1/2 on the outside, 2 over 3. Oh, those guys will cancel. Yeah, don't forget the 1/2 on the outside.
Okay. But that should
So
show over 3.
that would get me going from -1 to 5, which will just give me that going from -1 to 5. A lot easier to plug in. Oh, you know what? I made a little mistake here. That's not x, that is a u still. Is that right?
Did we
That's a little
change the-
mistake.
Yeah, we changed the value.
U, so now let's change it back. So this would be 2x plus 6, 2/3, going from -1 to 5. And let's jam.
16 cubed divided.
16 is 4 cubed is 64.
64. 64 over 3.
Plug in 5?
Well, that's right.
I just plugged in the 5. Is that right?
Yeah. 5.
5 times 2 is 10, plus 16 is plus 6 is 16.
Square root is 4.
Square root of 4, and then 4 times 4 times 4.
Oh, the cubed is outside. I thought the cubed was inside.
Subtract. Now we're going to plug in the -1 in here. -1 times 2 plus 6. I think we already know that's 8 over 2. Is that right?
And a 6 over 3?
But that's going to be 2, -2 plus 4 is a
4 cubed.
4. Square root of 4 is 2. And 2 times 2 times 2 is 8.
Yeah.
Okay, we got that. And then that's going to be 64 minus 8, anybody?
56?
56 over 3. Okay.
Minus-
Jamming. Okay, so I got myself, I think what I have is 56 over 3.
The answer is 2 over 3.
Did we plus or minus the 12?
Subtract.
Subtract the 12.
So minus 54 over 3.
And then what else were we adding
Oh,
from the other side?
12? Wait, no, what
Add
is it?
6.
Add
Well, the
6.
six- it was a
Yeah,
6.
minus
I
12
don't know
plus,
if it was
okay, yeah. So it's minus 18. No, it's not.
6, it's 50 over 3. Well, no.
Minus 6 over 3 is
I'm
minus
saying.
18 over 3, so it's 32. No,
Let's see, putting a 1 here, 1 there, right? Pretty good.
38. The answer is, wait, 56.
Just putting everything in terms of 3s here. Let's see, this would be minus 3 over 36 plus 3 over 18. Anybody? 56 minus 36 plus 18.
38? It's 38 over 3.
Okay,
Yeah.
I'm gonna
And
just
then
check
the
something.
60 over 3 from the beginning, so it's either 54 over 3 or it's negative. No.
Okay, you guys got what again?
38.
38 over 3?
And then are we adding or subtracting?
That was a long one.
We're not done, are we?
I don't know. Are we?
So
What
we
do you
still
guys
have
say?
16 over 3 from the first half.
Oh, true.
That's true, huh?
So is
Okay.
it 50,
Good
Over
Yeah.
3, or is it negative?
Let me go 16, right? 16 over 3 was from our first half, right?
You add them together.
We are at.
And adding them together because it's the two total area.
Well,
All right, 54 over 3, is that right?
16 different fractions of 3.
Answer is,
I'm fine.
54.
And I got a 56. I got it.
does 3 go into 54?
Yeah. Done.
Yeah,
18.
because it's 9 times 6.
What you with 18?
True, true, true.
It's 9 times 6, so.
What is 18 times 12 and add 6 again?
Yeah, 18 times 3.
This was, Owen's question is, why did we add 12, minus 12 and add 6? This is from our x squared over 2 antiderivative, and this was from our x derivative or antiderivative. Okay, sorry guys, 54 over 3, does that?
18.
18, okay, so it got an answer of 18. Crazy, okay.
But that's like an even number of
Nice,
square
even number.
units.
Uh-huh.
This is definitely a fabricated math problem.
Yep.
See, like what potentially like one of the worst jobs, like coming up with these problems.
Uh-huh, yeah, it is, yeah.
Seems terrible.
Okay, guys, let me show you something. Caps on real quick here. Think caps on, let's go. So same exact problem, same exact everything. We're gonna see it a little differently. Let's check this out. Exercise 4 is, guess what? It's find the enclosed area of this and this.
Oh, no.
Are we good? And let's graph it again.
Different interval?
Boom, boom, boom. There's my x minus 1. There's my top function, bottom function, everything good there so far? And we know that's true. We know that's true. And we know that's true. Everybody good there? Don't know what I did there. Let me see what I did there. So I think I'm just graphing it here, but let's see. Never mind on that here. Again, just solving for that right there. Oh, gotcha. Okay. Let's just want to see something real quick here. It was this area that we needed to do. Is that right? I'll catch up with that in just a second here. So don't mind that just for a second here. We were still supposed to do this area right there. Is that right?
Hey, good job, eh?
Okay, so thinking caps on just for a second here. Here's what we got. And we got 5 minutes. No, we got a little more than that. Notice we did top to bottom. Is that right? We had to cut it off right here, right? And make completely new things here. Is that right? But real quick here, instead of integrating it in terms of the x-axis, ready guys? Let's integrate it in terms of the y-axis. Whoa. So let's see. What's my rightmost function? This one here is. No, not top. You're thinking right and left.
I thought you were saying right.
Oh, the rightmost function would be what,
X minus one.
X minus 1. Perfect. And what's my leftmost function? Now notice real quick here. It's the parabola. Is that right?
See.
Notice real quick here. If I go from here to here, notice it does not change. The line is my left. The line is my right. The parabola is my left. We good?
Oh, the whole way up.
The whole way up. Now the only little thing is we can't do it in terms of dx. We're going to do it in terms of dy. So here's what we're going to do. We're going to solve each of these guys for the x value. So what do I do here to solve for x?
Add one.
Add. Uh-huh.
We like all say subtract one.
I think so.
Yeah, no
Yeah.
plus.
So let's see. If I, whoa, that was missing. Everybody okay with this right here? This is y plus 1. Okay, guys, real quick here. Let's solve the other one for x as well. If we solve the other one for x, it looks like this. I'm going to subtract 6 from both sides. Is that right? I'm going to divide by 2. Everybody okay with that?
Oh, that's okay.
And this is my rightmost function, and that's my leftmost function. Are we
Wait,
good?
that means you only get 2 functions.
Yes, I don't need to split it off. I could just do it in terms of functions only. We're good there.
So do you do the left function minus the right function, or do you do the other way around?
It's always right minus left. But if you did it left minus right, you just take the negation of it and you're going to be exactly where you want to be anyways. Okay, real quick here, guys. Let me go back to here. Zoom. So real quick here, since we know that and that, Guys, real quick here. We noticed that, remember how we noticed that this was a -1? We just had to plug in this guy into our straight line. If this is -1, -1 minus 1 was -2. Are we good? Because the straight line determines both of them, right? If this was a 5, we knew that was 5, right? If we plug a 5 in here, 5 minus 1 is a 4, because we need these guys. So we're going to integrate using dy from -2 to -4. You always want to integrate up. We good? Always integrate up. Uh-huh. And almost done, but let's go. Let's integrate this guy here. So we're going to go from -2 to 4, and now we have our rightmost function. Everybody agreed there? Minus my leftmost function. Let's see if we did that correctly here. Ah, sorry, real quick. It was on the previous slide. One sec, let me go back. No. It was right over here. Okay, you guys okay with that? Moving the 1 over? You guys are okay with moving the 6 over, dividing by 2? So it becomes technically -1/2, and then it's -3. That's cool. Okay, so we're integrating from, that's my left, that's my right. We're integrating from -2 to 4. And it's going to be my right minus my left. And then I can put this together. So what is that going to be together here? So that's y minus 1. That's going to be a -1/2 y squared. That's going to be a +3. So it's technically +4. Is that right? So, okay, let's do this here. So this is going to be -1/2 y squared. Plus y plus 4. Perfect. Okay. No need to split it off into 2 different pieces, right? A lot more. Hey, don't even need to do a u substitution here. This is just straight up antiderivatives and go. So let's jam. This is going to be y to the 3rd over 3. This is going to be y squared over 2. And this is going to be 4y. Going from -2 to 4, is that a lot more simpler than we did? I know you guys are brain are fried. I understand that. So we just took the antiderivative with respect to y. No need to do no new u substitution. No splitting it off into different pieces. Way more easy. So plugging in a 4 into there.
-1/2 times 64.
64 over -6. Plug it in the 4 over here. That makes 8. That makes 16. Subtract from, plug it in -2 into here. So -2 times -2 times -2. So let's see, that makes sense here. -2 times -2 times -2 is -8, right? But negative and a negative, and the negatives cancel, so 4 over 3. -2 into there makes 4, so 4 divided by 2 is just a 2. And -2 plugged in there makes a -8. Cool, let's simplify this as much as possible. So I got myself. Let's see, that's gonna be 4/3. That's gonna be minus 6. 6, is that right? 6 would be good.
So it's -36 thirds.
30. Yeah, minus 36/3, which technically would be 30 minus 18, or yeah, 12. Sorry, 12, which is. Oh, hold on. Did we get 8? Did we get 18 when we did it during the X's?
We did.
We did. Okay, so same stuff applies. Sometimes you can derive it using the Y values. We good? That is it.
I'm gonna run me in the bathroom line,
Go.
but
And watch out for the cords. Watch out for the cords. Okay. You got it, guys. Yep, absolutely. All right, guys, and enjoy the rest of your day.